Dear students, welcome to my YouTube चैनल आओ केमिस्ट्री सीखें। लेट्स एंजॉय केमिस्ट्री। आज हम केमिकल काइनेटिक्स का थर्ड लेक्चर पढ़ने जा रहे हैं। ये लेक्चर है इंटीग्रेटेड रेट इक्वेशन ऑफ सेकेंड ऑर्डर रिएक्शन। सो आओ केमिस्ट्री सीखें। लेट्स एंजॉय केमिस्ट्री। डियर स्टूडेंट्स, आज हम सेकेंड ऑर्डर रिएक्शंस के लिए इंटीग्रेटेड रेट इक्वेशंस डेराइव करने जा रहे हैं। So the first question comes, what are second order reactions? Suppose there is a reaction A plus B is equal to product. This reaction will be called as a second order reaction only when rate of this reaction will depend on two concentration terms. Now these two concentration terms may be of same reactant or of different reactants. So in both the cases, the reaction will be called as a second order reaction because in first case R is proportional to concentration of A power 2, that is R is equal to rate constant into concentration of A power 2, or in second case R is equal to rate constant into concentration of first reactant into concentration of second reactant. In first case, the rate is of second order in terms of A itself. That means it will be of zero order in terms of B. Only then it will be called as a second order reaction. And in second case, which is a more general case, the rate is of first order in terms of A as well as in terms of B. As a result, total order of this reaction also becomes 2. So, there are two types of second order reactions. Number 1, where both the reactants have same concentration. It is generally written as R plus R is equal to product. That means both the molecules of reactants are taken as same. The second case of second order reaction is the case where both the reactants have different concentrations, and it is generally written as R plus S is equal to products. Here both the reactant terms are taken different, one R and other S. Dear students, today we are going to derive the integrated rate equation for the second order reaction of first type where both the reactants have same concentration. It is generally written, as I told, as R plus R is equal to product. This in effect means that two molecules of same reactants are involved in the chemical reaction. Let us say initial concentration of the reactant is A, and with time what will happen? Concentration of reactant will decrease because it converts into product. So let us say at time t, the concentration of reactant decreases by x. So remaining concentration of reactant will be A minus x. Similarly, remaining concentration of second reactant, which is same in this case, will also be A minus x. Now, rate of reaction at time t will depend on the remaining concentration of reactant. Mathematically, it can be written as dx by dt. This is the rate of reaction will be proportional to A minus x into A minus x. So mathematically, we can write it as, in turn, can be written as k into A minus x whole square. This is the differential rate law for a second order reaction in which both the reactants have same concentration. Now we can obtain integrated rate equation by integrating this differential rate law. Before integration, we have to take like variables together. This is called as separation of variables. What we have to do to separate the variable? Here is the dx, that is a term with variable x. So we will bring this term, this is also with variable x, to left hand side, and we will take this dt to right hand side. This is known as separation of variables. So on separating the variables, we get equation something like this: dx upon a minus x whole square is equal to k into dt. Now, if you have gone through my lecture about integrated rate equation of zero order and first order reaction, you must have got the idea of the next step. Next step is integration of this equation. So on integration, we will get an equation like this. Since k is a constant on right hand side, so we are going to integrate only dt, not k. K is taken out of this integration sign. Now on integration, dx upon a minus x whole square gives 1 over a minus x, whereas dt on integration gives t, and we get an integration constant c along with all these integration terms. For the students who find integration difficult, I am going to integrate this dx over a minus x whole square. There may be more than one method to integrate it. I find the simplest one as this. Let this a minus x be equal to y. A on differentiation becomes 0. So we get minus dx is equal to dy, or dx is equal to minus dy. Now we have got dx upon a minus x whole square. So substitute the value of dx as minus dy and substitute the value of a minus x as y, because we have taken a minus x is equal to y. So it becomes y square. Now this can be rewritten as y power minus 2, because we have taken y from denominator to numerator, and dy is present here, and minus, it comes before y power minus 2. Now you must have got idea about integration of this term. If we want to integrate it, we have to integrate this term. This minus will come outside. Y power minus 2, on integration it becomes y power minus 2, and we have to add 1 here and divide by the new power. So it becomes minus y power minus 1 upon also minus 1. This minus minus becomes plus, and y power minus 1 comes to denominator as y power 1. Now substitute back the value of y as a minus x. So this is how we get integration of dx upon a minus x square as 1 over a minus x. Our next step is to find out the value of integration constant c. For this, we take a condition, and that condition is at the beginning of reaction, when time was 0, all the reactant was equal to A. The concentration of reactant was equal to A. So, at time t is equal to 0, A minus x, that is remaining concentration of reactant, was equal to initial concentration of reactant A. So if we substitute this condition here, so what we have to do, instead of a minus x, we have to substitute a. Instead of t, we have to write value 0. So this term becomes 0, or c is equal to 1 over a. This is the value of integration constant. Now we will substitute this value here. We will get a better equation like this: 1 over a minus x is equal to kt plus value of C is 1 upon A. So this is one form of integrated rate equation of second order reaction. We can rewrite it by taking Kt on one side and 1 over A on other side. So Kt is equal to 1 over A minus x minus 1 over A. In general, we write integrated rate equation in terms of K. So we have to take this T to right hand side. On taking T to RHS, we get the final equation as K is equal to 1 by T square bracket 1 over A minus x minus 1 over A square bracket closed. Now, what is A minus x here? It is the concentration of reactant at time t. And what is A? It is the initial concentration of reactant. So, this equation can also be written as K is equal to 1 by T inside bracket. It is written as concentration of reactant at time t minus 1 over concentration of reactant at time 0 or initial concentration. So this is another form of second order reactions integrated rate equation when both the reactants have same concentration. Now coming to examples of second order reactions. The typical example of second order reaction is dissociation of hydrogen iodide. The gaseous decomposition of hydrogen iodide gives hydrogen and iodine. The rate of this reaction depends on concentration of hydrogen iodide power 2. So, it is a second order reaction of first type where both the concentration terms involved in the rate are of one reactant. Coming to example of second type of second order reaction where two different concentration terms are involved in the rate law. Here one ester reacts with NaOH to give sodium acetate as the salt and ethanol. So it is the typical reaction known as saponification reaction, and rate of this reaction depends on concentration of ester as well as concentration of NaOH. So these are two examples of two different types of second order reaction. This is all about the second order reaction for the time being. Thank you.